Now, in the first section, we really highlighted chemical and physical properties. Today, what we're going to be doing is looking at chemical and physical changes. So, go and get your notes out, Jason. There, as you can guess, there is a difference, and what the changes, especially the chemical changes aspect, is what we tend to really focus on, and what we're going to focus on in this class as we proceed through the remaining part of this year. Okay, let's first talk about physical changes. Okay, is defined as a change that alters a substance without changing its composition, meaning it's a change that essentially changes the appearance of a substance. After a change, physical changes happen, it's still the same substance. It just might look a little different. Okay, chemically though, it is the same. Crumpling up a sheet of aluminum foil, crumpling up anything really. Okay. Before we crumple it, it's typically smooth, flat, pretty shiny, almost mirror-like. But after we crumple it up into a ball, it's now round, compact, okay, and it's in a ball shape. And even if we were to undo that crumpling to where we kind of flatten it out more, it's still not going to be identical necessarily in appearance to how it was before any change had been done to it. Okay, maybe some of the mirror has dulled off. It's obviously going to be more crinkled instead of flat. Okay, or if we cut a sheet of paper, okay, I cut a piece of paper in half. Each half is still going to be paper. Still going to have the same properties as it did before it was cut in half. Breaking a crystal, okay, it's still going to be that same crystal. Terms that we associate with physical changes often include, but are not limited to, the following: bending, grinding, I believe it's supposed to say crumple, splitting, crushing, anything that you can think of, as long as the end result is still the same substance. Now, in the end of the first section, we talked about changes of state. Solid, liquid, and gas going into all the other various states. Okay, we call those phase changes. Simply just a change from transition of matter from one state to another. Temperature and pressure changes will change the state of matter. We use the example of water when we were talking about this in section 1. Okay, at and below 0 degrees Celsius under atmospheric pressures, it is a solid. It's ice. As we heat it up, it begins to melt. And as it melts, it becomes liquid water. Then as we continue to heat, continue to raise that temperature to 100 degrees Celsius, we then have a transition between water to vapor. It begins to boil. Okay, now what's interesting is, as you measure the water temperature, typically at normal atmospheric conditions, you'll notice that measuring boiling water really won't go any higher than 100 degrees Celsius. Even though you're cranking in that heat, it will only go up to 100 degrees Celsius. The change of state is a physical change. Although in our example, ice, liquid water, and steam or vapor may be different in appearance, their chemical composition is still the same. It's still H2O. Okay. So when we talk about phase change, we like to use the terms boiling, freezing, melting, condensing. Now, boiling and melting are intensive properties. We talked about what an intensive property was in the first section. That means it is independent. I could have an ounce of water or a gallon of water. Each one of those amounts is still going to either boil or melt at the same temperature. And so having these intensive properties of water, we could possibly use that to help us identify an unknown substance. So if we didn't know it was water, we could boil it, we could melt it, we could freeze it, and measure the temperatures at which each one of those phase changes happens. And that is pretty unique in terms of those temperatures to water, but we could use those in identifying it. So that brings us into what we like to focus on in here, and that is chemical change. It is a process that involves one or more substances turning into a new substance, often referred to as a chemical reaction. Now, when we say a new substance, that means that new substance, after a chemical reaction has occurred, will have different compositions as well as different properties from substances before the reaction occurred. You have to have something new that is unique to what you had initially before anything happened. So, some terms that we often associate with a chemical change occurring: explode, rust, oxidize, corrode, tarnish, ferment, burn, rot. Again, the list goes on and on and on to help us indicate what process would be considered a chemical change. A very common example that is used to exemplify a chemical change would be rusting of iron. Okay. First of all, you have iron and you have oxygen. Okay. You think about it this way: they don't necessarily get along. Okay. Whenever they are introduced to each other, they begin to react. Okay, that's why they are called the reactants. Now, as iron and oxygen begin to react, we get this new kind of gross product, okay, known as rust. Okay. Now, rust is simply known as, or chemically known as, iron oxide. And so, if we look at the chemical reaction, which will show the relationship between the reactants and the products and who's interacting with whom, we see that Fe, which is iron, is going to react, that's usually what the plus sign means, with oxygen, O2, and that arrow means yields or produces, okay? Iron oxide. And more specifically, iron 3 oxide, but we'll get to how we identify that later on. So, how do we tell if there has been, in fact, a chemical change occurring? Okay. So, in order to have a chemical change, we have to have a chemical reaction. And this will always produce a change in chemical properties. Some signs that we might be able to tell if a chemical reaction has occurred include energy changes, changes in smell. Some not listed on here are production of gas bubbles, changes in color, light. Okay, oftentimes we mean fireworks. That's essentially a chemical reaction. See light. Okay, sound. Really, when you think about it, any of the major senses can help evaluate and indicate if a chemical change has occurred. So rust, a product, has different properties than iron and oxygen, which are the reactants. Again, we were told a few slides ago that in order for it to be a chemical reaction, the product must have different chemical properties. Okay. First of all, let's look at the reactants. Iron, typically silvery gray in color. You can attach a magnet to it. Oxygen is a gas. It's clear and colorless. Bring those two reactants together, you get rust. Rust is a nasty brown, orange color. It's considered powdery simply because it can break off and form smaller particles. Okay? But what's interesting is when you have the formation of rust, you can no longer have a magnet attract to it. So those changes in color and magnetism are pretty good indications that a chemical change has occurred. Now, one of the most, if not the most important thing when we talk about chemical change is this: the conservation of mass. And this is one of the many laws that we have to abide by in our natural world. Okay? The law of conservation of mass states that mass is neither created nor destroyed in a chemical reaction. What you have in the beginning, in terms of mass, you must have in the end. But you just might have it in a different ratio in terms of combinations and products. So, this was found when the mass was carefully measured before and after many chemical reactions. The total mass involved in the reaction always remained constant before and after the reactions. And so, because of this discovery, it made possible to measure by the scientific advancement of the analytical balance. And that's what we're going to be looking at today. Okay? Solving, calculating, verifying that we are obeying the law of conservation of mass. Okay? The equation for the law of conservation of mass is very simple. The mass of the reactants must be equal to the mass of the products. And if need be, you can use very basic algebra to help solve for an unknown substance. So how do we solve the law of conservation of mass problems? First, you determine what you know and what you don't know for the problem. Then you will write an equation showing the conservation of mass of reactants and products, substitute known values into an equation, and solve for the unknown. Think of it kind of like a balance itself, okay? Your left side, your reactants, must equal the right side, your products. If there's an imbalance there, then you can pretty much guarantee that you have gone against this law. Okay, something's wrong. Now, does anybody bake in here? Does anybody bake cookies? Has anybody been a witness to anybody baking cookies? I've never done that. We made shrimp in our air fryer last night. That was a huge mistake. Stinky. But anyway, let's talk about baking. Okay, so let's make some cookies. What do we have to have to bake cookies? Go to the store, man. Yeah, we have to have cookie dough, okay? Does anybody know what might go into cookie dough? I am not a baker. I just burned steamed broccoli last week, so yeah, I don't cook. Eggs? Flour, baking soda? Water? Maybe some milk, depending on the recipe. Maybe some oil. Okay? Maybe some chocolate. Butterscotch, whatever you want, right? Vanilla? So, we put all those ingredients in. Okay? You stir them up. What do you have? You've got this glop, right? This batter. Very liquid and viscous. You know what viscous is? Kind of thick, liquidy, like we would say like motor oil is viscous. Okay. What's that? What viscosity is? Well, it's coming back. So anyway, you've got this batter that's very liquid, okay? And I guess cookies are liquid. I'm thinking of cake, but anyway, you got a batter. You got cookie batter. You put it on the cookie sheet and put it in the oven, and out after a while pops cookies, right? Now, would you say that the cookies that you took out of the oven have the same chemical properties as the batter that you put in? Why do you say no? The big thing was you added heat. Heat really likes to jumpstart chemical reactions. Heat is energy. And one of the questions you can always ask yourself is, if you want to determine whether or not it was a physical or chemical changes, can you get your egg back? You can't get your egg back, can you? You can't put the cookies back in the oven and reverse the process and get your eggs back in your hand, can you? They've changed. They've changed chemically. They've changed, their protein structure has been changed. But you're definitely not getting it back after that. Let's talk about how we can relate baking cookies to this. Let's say before you put the cookie batter on the sheet and put it in the oven, you waited. And then you found out that, it's about, 16 ounces or so of batter, okay? But the entire thing of batter on a cookie sheet, put it in the oven, and you decide to weigh the cookies after they're cooled. You take them off there, put the cookies directly on there. You find that, it's maybe 15.7 ounces. Is that the same amount as that you put in? Mm-mm. Well, right off the bat, we might think, well, that doesn't follow the law of conservation of mass because we have a lower mass after we cook than when we started. What do you think happened? Why do we have a lower mass or a lighter mass? Although it's relatively small, why do we have that? What could have happened?
The moisture could have evaporated.
Aha! Very good. You put a lot of moisture in it, a lot of water. Okay? You add heat, which is typically, I guess cookies are like at least over 300. 298? Okay. Still above 100 degrees, right? Where does water typically boil and turn to steam? 212. Okay. 100 degrees Celsius, 212 degrees Fahrenheit. So you're still baking at a higher temperature. So what do you think is happening to that water? It's going from the liquid form in the batter to a gas form. That gas form is going out of that cookie and into your oven environment. And you open that door and that gas escapes. How much do you think that gas that escaped weighed? 0.3 ounces. So we didn't violate the law of conservation of mass. That's good. Otherwise, we'd be in weird situations. Okay? So, why I'm mentioning this is because not every chemical reaction is going to just be like this plus this. They're going to be equal. No matter what, we get a solid new product, good to go. Oftentimes, gases are formed as a product. And those gases have mass. And usually, most likely 100%, that gas that is formed will be kind of the missing mass after the year before and after measurements. So you really want to pay attention to what's going on in a reaction. So let's look at a couple problems before we wrap up our notes today. So in an experiment, 10 grams of red mercury 2 oxide powder is placed in an open flask and heated until it is converted to liquid mercury and oxygen gas. The liquid mercury has a mass of 9.26 grams. What is the mass of the oxygen formed in the reaction? Well, as you probably already guess, okay, what we have to do here. Okay, lighten up. All right. So, okay, where are we? We have 10 grams of mercury to oxide. Okay. It breaks down into 9.26 grams of mercury and how many grams of oxygen? Okay. So, how do we figure this out? Again, if you think about it as a teeter-totter or a balance, so we got to make sure that these are even. If our single or lone reactant has a mass of 10 grams, what must our product side equal? 10 grams. Okay? So, in order to solve for this, you know what I'm going to do? I'm going to do a little algebra. Okay? I'm going to subtract both sides by 9.26 grams. And so, I should have, when I do that, 10 minus 9.26, I should have 0.74 grams. And that is how much oxygen will be produced. Pretty straightforward, right? Okay, and these are just kind of introductory stuff. And that's what we're going to do after we do our next problem as well. But tomorrow, like I said, we're going to do even more. Next and final question for your notes. From a laboratory process designed to separate water into hydrogen and oxygen gas, a student collected 10 grams of hydrogen and 79.4 grams of oxygen. How much water was originally involved in the process? So I'm just going to write these numbers down. Okay, 79.4 oxygen. Okay. So our products in this case are the hydrogen and oxygen. Okay. So we started off with unknown amounts of water, and it yielded 10.0 grams of hydrogen, that's H2, plus 79.4 grams of oxygen, O2. What do I need to do to solve for how much water was initially present? In this case, we're just going to add 10 plus 79.4. We get 89.4 grams of H2O. Again, fairly straightforward. Questions yet? All right. So what I like about this worksheet is it not only goes through the law of conservation of mass, but it also kind of brings up the idea of, you know, the components of a chemical reaction. Okay. We may have only briefly at all discussed it this year, identifying reactants and products. And there's only like one question like that, but it's very important to us right now and our continued lessons in the remaining part of the year. Okay. So I'll go ahead and pass out this homework after I stop recording. Those of you at home, I will be posting this to Classroom in here just a minute. So, but I'm going to stop the recording.